Here we're going to describe behavior near the critical point and want to make clear what the critical point is. So the diagram of pressure versus temperature, so this is a projection of a three-dimensional pressure, volume, temperature phase space. Solid is at low temperatures, higher pressures, liquids in this region, vapor is this region, but keep in mind there's no dividing line here that distinguishes this region that we would call supercritical, where past this point we have supercritical. It's a continuum. If we look at the pressure, and this is log of volume projection, then what we're used to here is saturated liquid. That would be in equilibrium with saturated vapor. Above the critical point, we have supercritical fluid. We cannot have two phases present. And so the critical temperature is here, and then the critical pressure, and we use the critical temperature and pressure quite a bit to characterize materials. So the question is, what happens if we were to start with a fixed volume container? So liquid, vapor, and equilibrium, volume is fixed, and we're going to pick the volume such that the volume per mole, because this is a molar quantity, is the critical volume. In other words, take the entire volume, divide by the number of moles in the container, and we're right at the critical volume. So we're right here, the critical volume. It's only one component in the system. And then the question is, what happens if we heat this? Then on this diagram, we're going to stay along this constant volume line. And so what will we see when we heat such a system? Well, as you'll see in the video that follows, and what this video is showing is exactly this, a container. We're looking at the water, a metal container with a window that we can see through, and we're heating it up. And what we're going to see happens is that as we get to higher temperature, eventually this dividing line becomes fainter and fainter until we just have one phase. In other words, you can see from this diagram, as we get closer to the critical pressure, critical temperature, the difference between the saturated liquid here and the saturated vapor here decreases. Their volumes start to become similar, their enthalpies, all their other properties, until we get to this point where we only have one phase. And so as we heat it, essentially this disappears. We see it slowly disappears. We end up with just one phase, and that phase is a supercritical fluid. You know, in this demo, material is used that has the properties, the right critical pressure and the critical temperature, not too far above room temperature, to make it easy to do this demo. So watch this demo to see what happens. So the important thing to notice then is that we did not see a phase change. We just saw a smooth transition to the supercritical fluid as the properties of the liquid and the vapor became more similar to each other. That is, we didn't evaporate the liquid or condense the vapor by expanding the liquid. Instead, they became so similar until at the critical point they were identical. Now we'll look at a second video where we're going to cool. So we have now the supercritical fluid, the same system. I'm going to cool it. So in the demo, we actually cool it by pouring cold water over it. So you'll see water dripping down the outside. That's just a convenient way to do it. What we want to look at is what happens in the video. So as you saw, the behavior when we cooled was rather different in that as we passed through the critical point, essentially became opaque. So you observed that it became opaque. This is a phenomena referred to as critical opalescence, where essentially we have large density fluctuations, and these scatter visible light, and then we eventually end up with separation in two phases that we originally started at in the first part of the first demo. But as we pass through that critical point, as we start up here and as we pass through, then we start seeing that we get these large density fluctuations.